Tonight, we're going to look at the number that changes how you think about everything in the night sky. Our galaxy contains 400 billion stars. Most people hear that and picture something dense, a structure packed with light and matter, star after star filling the space between here and the edge of the Milky Way. The reality is the opposite. 400 billion stars, and the galaxy is still almost perfectly empty. The stars are so spread out that what we call a galaxy is really the empty space, with a few stars scattered through it. The vast majority of the Milky Way has never been touched by a planet, a moon, or anything solid at all. By the end of tonight, you're going to understand where that emptiness comes from, why the stars ended up so impossibly far apart, and what that distance tells us about the way the universe has been building itself since the very beginning. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The average distance between stars in our part of the galaxy is roughly 4 to 5 light years. 4 to 5 light years of empty space between one star and the next. That is the average gap, not some exceptional void between unusual neighbors. Just the normal, everyday separation between the stars you see when you look up on a clear night. And 4 light years, even though it sounds like a tidy astronomical number, is a distance so vast it essentially breaks every intuition we have about crowded spaces. Light, the fastest thing that exists, travels at about 186,000 miles per second. In 1 year, moving at that speed, every single second, without pause, light covers about 5.88 trillion miles. In 4 years, it covers roughly 23.5 trillion miles. That is the gap between our Sun and Proxima Centauri, the nearest stellar neighbor we have. 23.5 trillion miles of empty space. And that is the closest one. Every other star is farther. So when we say a galaxy contains hundreds of billions of stars, we have to immediately reckon with what it means that each one of those stars sits in the middle of its own vast bubble of emptiness, separated from every other star by a gulf that light itself takes years to cross. The question of why galaxies are mostly empty is really the question of why that gap exists at all. Why aren't the stars packed closer together? Why is there so much nothing between them? The answer starts long before any star existed, back at the very beginning of how galaxies form. In the early universe, not long after the Big Bang, the cosmos was filled with enormous clouds of hydrogen and helium gas. These clouds were not uniformly dense. There were tiny fluctuations, regions slightly denser than their surroundings, and regions slightly less dense. Those density differences, even though they were incredibly small, about 1 part in 100,000, were enough for gravity to work with. Gravity pulled matter toward the denser regions. Over millions of years, and then hundreds of millions of years, those slightly overdense regions grew denser still, collapsing inward, pulling in more gas, growing more massive, pulling harder. The gas clouds that eventually became galaxies were enormous, spanning hundreds of thousands of light years. They contained enough material to build hundreds of billions of stars. But here is the critical point. Those clouds were also rotating. As a cloud collapses under gravity, any slight rotation it had to begin with gets amplified. The same principle that makes a spinning figure skater speed up when they pull their arms in. The cloud flattens into a disk as it collapses, spinning faster as it shrinks, and the material within it settles into a rotating structure. Within that structure, smaller pockets of gas became denser and hotter, eventually collapsing further under their own gravity to ignite nuclear fusion and become individual stars. But here is the thing that determines everything about the spacing. The gas cloud was enormous. The pockets of collapse within it were small and scattered, and the vast majority of the cloud's volume was just gas, too spread out, too thin to ever collapse into a star on its own. Stars don't form everywhere in a cloud. They form in specific pockets where local conditions allow it, and those pockets are separated by the same vast emptiness that characterized the original cloud. The spacing between stars today is, in a fundamental sense, an echo of the spacing between the star-forming regions in the original collapsing gas cloud billions of years ago. The galaxy didn't fill up with stars and then have gaps between them. The gaps were there first. The stars formed inside them at isolated points. That is why the galaxy is mostly empty. Not because something removed material from between the stars, but because that material never became stars in the first place. To really feel the weight of this emptiness, you have to try to think about it in terms of actual scale, even knowing that the numbers will resist any intuition you try to apply to them. Our Sun is about 864,000 miles across. It is, by every measure of daily life, an enormous object. And yet, if you placed our solar system next to the distance from our Sun to Proxima Centauri, the solar system would look almost impossibly small. Neptune, at its farthest, orbits about 2.8 billion miles from the Sun. Proxima Centauri sits roughly 23.5 trillion miles away. The entire span of our solar system out to Neptune is less than 0.02% of the distance to the nearest star. The stars themselves, all of them combined, occupy a vanishingly small fraction of the galaxy's total volume. Here is a way to appreciate just how extreme this is. Imagine compressing the Milky Way down to a scale where the entire galaxy fits inside a circle 100 feet across. At that scale, each individual star would be smaller than an atom. Not a small object, not a grain of sand. Smaller than an atom, and these subatomic specks, representing stars, would be scattered across that 100-foot disk with average separations of roughly a few millimeters between neighbors. A few millimeters of empty space between atom-sized stars across a 100-foot disk. That is the density of the galaxy. And the galaxy is one of the denser regions of the universe. This is not a quirk of the Milky Way. It is a fundamental feature of how stars form and how galaxies are structured everywhere we look. Now, there is a subtlety here that matters enormously. The galaxy is not uniformly sparse. The emptiness varies in a way that tells you something important about how galaxies work. Near the center of the Milky Way, in what astronomers call the galactic bulge, stars are packed far more densely than in the outer regions where we live. Our Sun sits in a region called the Orion's Spur, a minor arm connecting two larger spiral arms, about 26,000 light-years from the galactic center. Out here, stars are comfortably spread with average spacings of several light-years. But deep in the galactic bulge, closer to the central core, the density of stars increases dramatically. Near the galactic center itself, average stellar separations drop to fractions of a light-year. In some of the densest regions, stars may be separated by only a few light weeks or even light days. These are still enormous distances by any human standard. But compared to our neighborhood, the central bulge is almost unimaginably crowded. If you lived on a planet near the galactic center, your night sky would be spectacular beyond description. There would be so many nearby bright stars that the sky would never go fully dark. Thousands of stars would outshine anything we see from Earth. The darkness we associate with nighttime would simply not exist, and the danger level would be correspondingly higher. More nearby supernovas, more intense radiation, more gravitational disturbances from close stellar encounters. The relative quiet of our location, in the suburbs of the galaxy, is actually one of the conditions that makes stable planetary systems, and potentially life, more likely. We live in one of the emptier parts of an already mostly empty structure, and that emptiness may be part of why we're here to notice it. There is a structure at the very center of the Milky Way that is worth pausing on, because it sits at the densest point of the entire galaxy and shapes the dynamics of everything around it. At the core of the galactic bulge, hidden behind dense clouds of gas and dust, sits Sagittarius A, a supermassive black hole with a mass roughly 4 million times that of our Sun. 4 million solar masses compressed into a region smaller than our solar system. Astronomers have tracked individual stars orbiting Sagittarius A at extraordinary distances and extraordinary speeds. One star, designated S2, orbits so close to the black hole that at its nearest approach, it moves at roughly 2% of the speed of light. 2% of the speed of light for a star. Those close orbits are only possible because the density of material near the galactic center is so much higher than anywhere else in the galaxy. But even there, even in that most crowded region, the stars are not touching. They are not remotely close to touching. Even S2, whipping around a supermassive black hole at a fraction of light speed, has a clear path through space with nothing physically between it and the black hole but emptiness. The density near galactic centers gives rise to dramatic events: stars being torn apart by tidal forces, gas falling into the black hole and releasing enormous energy, jets of material blasting out along the rotation axis. But individual stellar collisions are still exceptionally rare, even there. The stars are still overwhelmingly separated by space. The difference between the galactic center and our neighborhood is a difference in the probability of a close encounter, not a change in the fundamental character of the emptiness. It is denser. But it is still, almost entirely, nothing. Here is where the numbers become important in a very specific way. The Sun has a diameter of 864,000 miles. The distance to Proxima Centauri is roughly 23.5 trillion miles. If you divide those two numbers, the size of the Sun versus the distance to the nearest star, you get a ratio of about 1 to 27 million. The Sun's diameter is 1/27 millionth of the distance to its nearest neighbor. To put that another way, if the Sun were the size of a golf ball sitting on a table in front of you, Proxima Centauri would be another golf ball sitting about 765 miles away. 765 miles. Two golf balls, 765 miles apart. And in between them, nothing. That is the average situation for stars in our part of the galaxy. And our solar neighborhood is not unusual. It is not some special void or gap. It is typical. This ratio, the vast disproportion between the size of a star and the distance to its neighbor, is the same fundamental fact repeated hundreds of billions of times across the galaxy. Stars are small. Distances are enormous. The galaxy is almost entirely the distance, not the stars. Let's go back to what is actually in all that empty space between the stars. Because saying it is empty is not entirely accurate. The space between stars is not a perfect vacuum. It contains what astronomers call the interstellar medium, a diffuse mix of gas, dust, magnetic fields, and radiation that fills the spaces between stellar systems. The interstellar medium is extraordinarily thin by any standard we could measure in a laboratory. In the regions around our Sun, the density of the interstellar medium runs to about 1 atom per cubic centimeter. 1 atom per cubic centimeter. A cubic centimeter is roughly the size of a sugar cube. The air in the room around you contains something like 27 million trillion atoms per cubic centimeter. The interstellar medium has one. That is the kind of vacuum that engineers and physicists on Earth spend enormous effort trying to create in specialized laboratory conditions. Out in space, it is just the default state of things between stellar systems. And even that thinly distributed gas is not uniform. It comes in different phases, different temperatures, different densities, organized by the physics of stellar radiation and magnetic fields and the shock waves from supernovas. Closest to hot young stars, the gas is ionized electrons stripped from their atoms by intense ultraviolet radiation. These regions of ionized hydrogen, called HII regions, after the shorthand for ionized hydrogen, glow with a characteristic red light. They are among the most visually striking objects in astronomy. Vast nebulae lit up by the radiation of the stars forming inside them. Farther from hot stars, the gas is cooler and neutral hydrogen and helium atoms drifting along without enough energy to ionize. In the coldest, densest pockets, the gas cools enough for hydrogen atoms to pair up into molecules, forming what are called molecular clouds. These molecular clouds are among the densest regions of the interstellar medium, though that word dense is still relative. Even a dense molecular cloud contains perhaps 1,000 molecules per cubic centimeter, still a vacuum far superior to anything we can produce on Earth, but dense enough by interstellar standards for gravity to begin pulling the material together. These are the places where new stars form. The molecular clouds collapse, fragment, heat up, and eventually ignite, and the cycle of stellar birth continues. The interstellar medium is not just passive filler between the stars. It is the raw material from which stars are made, the environment shaped by stars as they live and when they end, and the reservoir that the galaxy draws on to continue building new stellar systems. The emptiness between stars is not dead space. It is a slow, cold, incredibly diffuse engine of stellar creation. There is something remarkable about how the interstellar medium is structured at larger scales, and it connects directly to why galaxies look the way they do. The medium is not uniform across the galaxy. It exists in a kind of rough equilibrium between different phases, maintained by the ongoing energy input of stars. When a massive star ends its life in a supernova, and supernovas are among the most energetic events in the universe, releasing more energy in a matter of seconds than our Sun will produce across its entire 10 billion-year lifetime. The explosion drives a shockwave outward into the surrounding interstellar medium. That shockwave sweeps up gas and dust. It compresses some regions, triggering new star formation. It heats other regions to millions of degrees, creating vast bubbles of hot, thin plasma that expand outward and push against the surrounding cooler gas. These hot bubbles can persist for millions of years before they cool and collapse. And supernovas are not rare on galactic timescales. In a galaxy like the Milky Way, A supernova occurs somewhere in the galaxy roughly once every 100 years or so. Over the life of the galaxy, that adds up to perhaps hundreds of millions of supernova events, each one churning the interstellar medium, driving shockwaves, heating gas, triggering new star formation. The interstellar medium is constantly being stirred, heated, compressed, and expanded by the stars living within it. And the end result of all that energy input and all that churning is still, fundamentally, an almost perfect vacuum. Because even the compressed gas in a supernova shockwave is thin beyond imagination by terrestrial standards. Even the densest molecular clouds are thinner than any vacuum we can produce in a laboratory on Earth. The churning just rearranges the distribution of this near nothingness. The fundamental emptiness remains. Now here is something that makes the emptiness even more profound. Everything we have discussed so far, the stars, the gas, the dust, the planets, all of it together, makes up only about 5% of the total mass and energy content of the universe. Roughly 27% is what astronomers call dark matter, and about 68% is dark energy. Dark matter is particularly relevant to understanding galaxy structure. It doesn't emit light. It doesn't absorb light. It doesn't interact with the electromagnetic spectrum in any way we can directly detect. But it has mass, and mass curves space-time, and so dark matter exerts gravitational influence on everything around it. When astronomers measure the rotation of galaxies, how fast stars at different distances from the center orbit, the numbers don't match what the visible matter alone would predict. Stars in the outer regions of galaxies orbit much faster than they should, if only the visible stars and gas were providing the gravity. The only explanation that fits the observations is that galaxies are embedded in enormous halos of dark matter, halos that extend far beyond the visible edge of the galaxy, contributing the extra gravitational pull that keeps outer stars moving at the speeds we observe. If dark matter were not there, galaxies as we know them could not exist. The outer stars would have too much velocity relative to the gravitational pull of the visible matter. They would fly out of the galaxy. The disk would disperse. Dark matter is what holds the structure together. The Milky Way's dark matter halo extends perhaps 600,000 light-years from the galactic center far beyond the visible disk of stars, which spans about 100,000 light-years. Most of the Milky Way's total mass is dark matter. The stars, as impressive as they are a relatively minor component of the galaxy's total mass budget. So when we talk about the galaxy being mostly empty, we have to be careful about what we mean. The space between stars is not entirely empty of ordinary matter. The interstellar medium is there, and the space between stars, and even far beyond the visible galaxy, is permeated by dark matter distributed in its vast halo. The emptiness is real in terms of the ordinary matter we can see and touch and measure with light. But the gravitational landscape of the galaxy is shaped by something we cannot directly observe, filling regions that appear to our telescopes to be completely vacant. The galaxy is mostly empty of luminous matter. It is mostly filled with something we do not fully understand. Let's step back even further and think about what happens when you zoom out beyond individual galaxies. Because the emptiness we find inside a galaxy is nothing compared to the emptiness between galaxies. The Milky Way is part of a collection of galaxies called the Local Group, roughly 80 galaxies of various sizes bound together by their mutual gravity, spread across a region about 10 million light-years across. The nearest large galaxy to us is Andromeda, sitting about 2.5 million light-years away. 2.5 million light-years of intergalactic space separating the two largest members of our local neighborhood. And the local group itself is a small, quiet corner of a much larger structure, the Laniakea supercluster, a vast web of galaxy clusters spanning about 520 million light-years and containing around 100,000 galaxies. When astronomers map the distribution of galaxies across the universe, the pattern that emerges is something called the cosmic web. Galaxies are not scattered randomly. They cluster along filaments, long, thin threads of matter, stretching for hundreds of millions of light-years. These filaments intersect at nodes where the largest galaxy clusters congregate, and between the filaments are the voids. The cosmic voids are regions with very few galaxies. They are not completely empty, but the density of galaxies is dramatically lower than in the surrounding filaments and walls. The largest known void, called the KBC void, named for the astronomers who studied it, extensively spans roughly 2 billion light-years. Inside it, galaxies are far scarcer than in the surrounding cosmic structure. Our own local group may actually be located within a relatively underdense region of the universe. These voids make up roughly 80% of the universe's total volume. 80%. The galaxies, clusters, and filaments, all the structure we find most interesting. All the places where stars and planets, and potentially life exist, occupy only about 20% of the universe's volume. The other 80% is vast, nearly empty space. The galaxy is mostly empty, compared to a densely packed laboratory vacuum flask. But the intergalactic voids are mostly empty compared to the galaxy. And even those voids are not absolute vacuums. The intergalactic medium, an even thinner version of the interstellar medium, drifts through them. Individual atoms of hydrogen, sparse beyond anything we could imagine, but present. The universe does not contain any true perfect vacuums, but it contains spaces so close to nothing that the distinction barely matters. The cosmic web itself is one of the most remarkable structures in the universe, and understanding why it looks the way it does helps clarify why the galaxy is the way it is. In the very early universe, in the first fractions of a second after the Big Bang, the distribution of matter was almost perfectly uniform. Almost, but not quite. There were tiny quantum fluctuations, random variations in density at subatomic scales. As the universe expanded and cooled, these fluctuations were imprinted on the distribution of matter at larger and larger scales. Regions that were slightly overdense began to gravitationally attract more matter. Regions that were slightly underdense began to lose matter to their denser neighbors. This process of gravitational amplification played out over hundreds of millions of years, producing the cosmic web we observe today. The filaments are the collapsed remnants of what were originally flat sheets of matter in the early universe. The voids are the regions that lost their matter to the surrounding overdensities. The galaxy clusters at the nodes of the web are the points where multiple filaments intersected and matter accumulated in enormous quantities. And within each galaxy, on smaller scales, the same process played out. Individual star-forming clouds collapsing under their own gravity within the larger collapsing structure of the galaxy itself. The emptiness at every scale within galaxies, between galaxies, across the cosmic web, traces back to the same fundamental origin. Tiny quantum fluctuations in the early universe that gravity amplified over billions of years into the structure we see today. The universe is hierarchically empty. empty within galaxies, emptier between them, and emptiest of all in the great cosmic voids that dominate the observable universe's volume. And all of it is the direct mathematical consequence of gravity acting on matter over cosmic time, starting from a nearly uniform distribution and producing everything we see. There is a question that comes naturally out of all of this, and it is worth sitting with. What exactly is going on when two galaxies collide? Galaxies collide. It happens. Andromeda is currently approaching the Milky Way at roughly 246,000 miles per hour and will begin a prolonged interaction in about 4 billion years that will eventually result in the two galaxies merging into a single large structure. But when people hear that two galaxies will collide, the image that comes to mind is usually something like a catastrophic crash, stars slamming into stars, planets disrupted, everything upended in fire. That is not what happens. Because of the vast emptiness we have been discussing, galaxy collisions are almost entirely the passage of two enormous clouds of nearly empty space through each other. The stars in both galaxies are so sparsely distributed that the probability of any individual star physically colliding with another star during the entire merger process is essentially negligible. The distances between stars are so large compared to the sizes of the stars themselves that even when two galaxies interpenetrate, the actual stellar components of each galaxy pass through the stellar components of the other without touching. It is, in a sense, two ghosts walking through each other, each galaxy barely registering the physical presence of the other in terms of actual matter contact. What does happen during a galaxy merger is gravitational. The gravity of each galaxy pulls on the stars and gas of the other. Orbits are disrupted. Stars that had been following stable paths around their galactic center find those paths altered by the gravitational influence of hundreds of billions of additional stars suddenly nearby. Tidal forces stretch both galaxies, pulling long streams of stars, called tidal tails, out into intergalactic space. Gas clouds are compressed by the gravitational interaction, triggering intense bursts of star formation. The two galactic centers, each harboring a supermassive black hole, gradually spiral toward each other and eventually merge. The whole process takes hundreds of millions of years, unfolding in slow motion on timescales that dwarf anything in human experience. But throughout all of it, the fundamental emptiness remains. Two mostly empty structures passing through each other, their contents rearranged by gravity, their stars almost never actually touching. The collision of galaxies is, at its core, a collision of gravitational fields, not of solid matter. And that is only possible because the galaxies are mostly empty in the first place. Let's stay with the merger scenario for a moment, because it illustrates something important about the specific nature of galactic emptiness. During the interaction between two large galaxies, the most dramatic physical effects are not star-star interactions, but gas-gas interactions. The interstellar medium of each galaxy can interact directly with the interstellar medium of the other. When two gas clouds collide at high speeds, they don't just pass through each other the way stars do. Gas can compress. Gas can radiate energy away and cool. And when gas compresses and cools, it can collapse under gravity and form stars. This is why galaxy mergers are often accompanied by starbursts, periods of dramatically accelerated star formation triggered by the compression of interstellar gas during the gravitational interaction. In some merging galaxy systems, the rate of star formation reaches tens or hundreds of times the normal rate. Enormous numbers of new stars ignite across the merging system as the compressed gas rapidly collapses. But even during a starburst, even in the most active star-forming region of a merging galaxy system, the stars being formed are tiny, isolated objects in an enormous volume of space. The starburst does not fill the galaxy with matter. It creates new point sources of light scattered across the same vast emptiness. The ratio of star to space remains almost exactly what it was before. The galaxy, after a merger, is brighter and more active, but it is not less empty. The emptiness is structural, fundamental, and essentially permanent on any timescale relevant to the stars themselves. Now, the spiral arms of galaxies deserve their own careful look because there is often a misconception worth clearing up. When we look at photographs of spiral galaxies, the sweeping arms of a galaxy like the Whirlpool Galaxy or NGC 1232, those elegant curved structures lit up with the blue light of young massive stars, it is easy to get the impression that the spiral arms are dense walls of stars, packed tighter than the space between them. They are not. The spiral arms are regions of slightly higher stellar density, yes. But more importantly, they are regions of active star formation. The spiral arms are bright, primarily because they contain young, massive, extremely luminous stars. Stars that burn hot and blue and shine with dozens or hundreds of times the light output of a star like our Sun. These stars are so luminous that they dominate the visual appearance of the arm, even though they represent just a small fraction of the stars within it. The arms also contain the molecular clouds and gas that feed star formation. Gas flowing through the galaxy gets compressed as it passes through the arms like a traffic slowdown on a highway, where cars pile up temporarily in a region even though they keep moving through. The material slows, compresses, and triggers new star formation. Then, the newly formed bright stars light up the region. But the stars themselves, including the faint, long-lived stars that make up most of stellar mass, are not dramatically more densely packed in the arms, versus between the arms. The arms are a feature of the gas distribution and recent star formation history. They are not solid walls of matter. They are waves of activity moving through a disk of stars. Our Sun is currently between spiral arms, in a minor spur called the Orion Spur, and the emptiness of our neighborhood is, if anything, slightly greater than it would be deep in a major arm. But the difference is modest. Everywhere in the galaxy, the stars are separated by light years. Everywhere in the galaxy, the overwhelmingly dominant substance is not star, not gas, but nothing. There is a perspective that astronomers have come to appreciate more deeply in recent decades, as our tools for mapping the galaxy have improved. The Gaia space mission, launched in 2013 by the European Space Agency, set out to measure the precise positions and distances of over 1 billion stars, roughly 1% of all the stars in the Milky Way. By 2022, Gaia had released data on more than 1.8 billion stars. Positions, distances, three-dimensional locations. Proper motions showing how each star moves through space relative to its neighbors. The result is the most comprehensive three-dimensional map of our galactic neighborhood ever constructed. And what it shows, more clearly than anything before, is the texture of the emptiness. Between the known star positions, you can see the voids, the regions where no star sits for light years in every direction. The map reveals that the Milky Way is not a uniform disk of stars, but a complex, sculpted structure with regions of higher and lower density, streams of stars following ancient orbital paths, clusters of young stars near their birth sites, older stars dispersed across the disk. But through all of that complexity, the dominant feature of the map remains the space between things. The gaps, the distances, the light years of nothing separating each point of light from every other. Gaia has given us the most precise picture we have ever had of the galaxy, and what it most precisely shows is how much of the galaxy is not there. Each data point in the Gaia catalogue is a star, a world with its own gravity, its own light, its own potential system of planets. And between each data point and its neighbors, in every direction, there is a gap so enormous that the fastest object in the known universe would take years to cross it. The catalogue is an inventory of islands in an ocean that is almost entirely water. Let's push deeper into the physics of star formation. Because understanding why stars form only in isolated pockets and not everywhere is central to understanding why the emptiness persists. For a cloud of gas to collapse and form a star, several conditions have to be met simultaneously. The cloud has to be dense enough that its self-gravity exceeds the thermal pressure pushing outward. The cloud has to be able to radiate away the heat generated by compression. If it can't cool, the pressure builds up and halts the collapse. The cloud has to overcome the support provided by magnetic fields threading through it. And the cloud has to be in a region of the galaxy where the tidal forces from neighboring matter and the general gravitational field of the galaxy don't shred it apart before it can collapse. These conditions are not easy to meet simultaneously. In fact, across most of the interstellar medium, they are not met. Most of the gas in the galaxy is too warm and too diffuse to collapse under its own gravity. Only in the cold, dense molecular clouds, the rarest and most extreme environments in the interstellar medium, do conditions come together in a way that allows star formation. And even in molecular clouds, only a small fraction of the cloud actually collapses into stars. The efficiency of star formation, the fraction of a molecular cloud's mass that ends up in stars, is typically only about 1 to 3%. 1 to 3%. The rest of the cloud disperses, blown away by the radiation and stellar winds of the newly formed stars, or simply too diffuse to collapse further. This means that even the densest, most active star-forming regions in the galaxy are only converting a tiny fraction of their available material into stars. The raw material for stars exists in vast quantities spread across the galaxy. But the process of actually making a star is inefficient, localized, and slow. It requires very specific conditions of density, temperature, and turbulence to come together just right. And when it does work, the resulting star is a small, hot, dense object surrounded by enormous amounts of space that weren't quite right for the collapse to happen. The inefficiency of star formation is another way of saying that most of the galaxy stays gas and emptiness rather than becoming stars. The conditions for stellar collapse are exceptional. The default state of galactic material is diffuse and spread out. Stars are the exception. Emptiness is the rule. There is one more component of the star formation story that deserves attention, and it has to do with the role of feedback. When stars form, they immediately begin changing their environment in ways that make it harder for more stars to form nearby. Massive stars emit intense ultraviolet radiation that ionizes the surrounding gas, heating it and driving it away from the star-forming region. The stellar winds from massive stars, streams of charged particles blowing outward at several 100,000 miles per hour compress some surrounding gas and disperse other portions. And when those massive stars end their lives in supernovas, the explosions drive shock waves outward that heat and disperse the remaining molecular cloud material. This self-regulation stars forming and then immediately acting to prevent further star formation in their vicinity is one of the primary reasons star formation efficiency is so low. The stars themselves, almost as soon as they ignite, begin clearing out the space around them. They push the raw material of future stars away. They ionize and heat gas that might otherwise have cooled and collapsed. They carve enormous bubbles of hot, thin plasma in the interstellar medium. And those bubbles, called superbubbles, when multiple supernovas overlap to create especially large structures, can span hundreds of light years. Our own solar neighborhood may be inside one such old superbubble, a region called the local bubble, a cavity of relatively hot and thin interstellar medium extending several hundred light years in multiple directions. This bubble was probably carved out by a series of supernova explosions over the past few tens of millions of years, and our solar system moved into it at some point in its orbit around the galaxy. The local bubble is emptier than the interstellar medium outside it, which means we live inside a relatively empty region of an already mostly empty galaxy, inside an arm spur that is already between the denser arms, inside a galaxy that is already almost entirely empty space. The emptiness is layered. Each layer is emptier than the one above it. We should spend a moment with what it actually means to exist inside this emptiness, not near Earth, not near any star, just somewhere in the middle of the galaxy, between stellar systems, in open interstellar space. The nearest star might be 2 or 3 light years away in some direction. A faint point of light in the darkness, probably not even the brightest thing in your sky. All around you, stars. Thousands of them, visible with the naked eye, just as you see them from Earth. But every single one of those points of light is years away. Some are decades away. Some are centuries. The light coming from them left before you were alive, before your parents were alive, before entire generations of human civilization. And you are sitting in between them, in the cold, dark space that connects them. The interstellar medium is there, perhaps 1 atom per cubic centimeter drifting past you. But for any practical purpose, you are in a vacuum more complete than anything that has ever been artificially produced on Earth. The temperature of open interstellar space set by the cosmic microwave background radiation, the ancient afterglow of the Big Bang, is about -454 degrees Fahrenheit, or -270 degrees Celsius. That is just under 3 degrees above absolute zero. The coldest cold we know. In that space, almost nothing is happening. Individual atoms drift. Occasional cosmic rays, high-energy particles, flash through. The magnetic field of the galaxy, diffuse and ancient, threads through the gas. Light from distant stars travels past in all directions. And that is it. That is what the vast majority of the Milky Way actually is. Not the spectacular nebulae in astronomy photographs. Not the dense star clusters. Not the dramatic spiral arms lit up with hot blue giants. Just cold, dark, empty space, with a single atom here and there, and the faint light of distant stars crossing the void. Those extraordinary images you see of nebulae, glowing clouds of gas lit up in brilliant reds and blues and greens, represent an extraordinarily tiny fraction of the galaxy's volume. They are the exceptions. The stunning exceptions, yes, but exceptions. The rule is the cold, dark space between them. Now let's think carefully about the actual volume of the Milky Way, because the numbers here are staggering. The Milky Way disk is roughly 100,000 light-years across and about 1,000 light-years thick in our neighborhood, though thicker in other regions. Its total volume is difficult to calculate precisely. The galaxy has no sharp edge. It just thins out gradually. But a rough estimate for the disk alone gives something on the order of 1 trillion cubic light-years. 1 trillion cubic light-years of volume. And within that volume, there are somewhere between 200 billion and 400 billion stars. Even if we take the high estimate of 400 billion stars, and even if we generously estimate that each star's gravitational sphere of influence, the region of space most strongly dominated by its gravity, extends to a radius of about 3 light-years. The total volume of space occupied by stellar gravitational zones would be a small fraction of the galaxy's total volume. The overwhelming majority of the disk's volume, the vast majority, lies in the gaps between those zones. Interstellar space, unowned by any star, dark, cold, nearly empty. And this calculation doesn't even account for the galactic halo. The vast, spherical region surrounding the disk that extends perhaps 100,000 light-years in every direction from the galactic center. The halo contains far fewer stars than the disk. Its volume is enormously larger. The halo is emptier still. If you drew a sphere around the galaxy large enough to contain the dark matter halo, perhaps 600,000 light-years in radius, the total volume would dwarf the disk volume by many times. And that entire extended region has even fewer stars per cubic light-year. The galaxy is not just a disk of stars. It is a disk of stars inside a vast spherical bubble of dark matter extending hundreds of thousands of light-years in every direction. And the disk itself is mostly empty. And the halo is almost completely empty. The Milky Way is, in total, more space than almost anything else. Here is where the question becomes genuinely philosophical. Why do we find the emptiness surprising? We live on a planet, a solid object, dense, full of matter, with continuous material, from the surface you stand on to the core deep below. Everything in our daily experience is matter pressed against matter. Objects touching, adjacent, filling space. We evolved in an environment where emptiness is the exception, where air and water and ground surround us constantly. Our intuition about what a full thing looks like comes from that experience. So when we hear that a galaxy contains hundreds of billions of stars, our minds build an image of something crowded. Stars everywhere. A dense field of glowing objects. But that intuition is built for a world of human scales, not cosmic scales. At the scale of galaxies, the stars are not crowded. They are not even close to crowded. They are so far apart that the matter making up each star is an almost insignificant contribution to the total volume of the structure that contains them. The Milky Way is, by volume, more than 99.99999% empty space. The fraction of its volume occupied by actual stellar material, the plasma inside each star, is so small that the number requires many nines after the decimal point to express. The galaxy is not mostly stars with gaps between them. The galaxy is mostly gaps, with occasional stars. That is the reality. And the reason it feels counterintuitive is not that the universe is being strange. It is that our intuitions were built for scales where this kind of emptiness never appears. At human scales, matter is everywhere. At cosmic scales, matter is almost nowhere. Let's push this one step further. Because even within the stars themselves, the densest ordinary objects in the galaxy, the story of emptiness continues. A star is essentially a ball of plasma, hydrogen, and helium gas, so hot and dense that the atoms are stripped of their electrons and the nuclei fuse in the core. The Sun's core reaches temperatures of about 27 million degrees Fahrenheit, or roughly 15 million degrees Celsius, and densities of about 150 grams per cubic centimeter, about 13 times denser than lead. That sounds solid and packed, but at the subatomic level, even stellar plasma is mostly empty space. An atom is almost entirely empty. The nucleus, containing nearly all of the atom's mass, occupies a tiny fraction of the atom's volume. If an atom was scaled up to the size of a large sports stadium, the nucleus would be roughly the size of a marble at the center of the field. The electrons orbit in a vast shell around that tiny nucleus. Everything in between the overwhelming majority of the atom's volume is empty space. This means that even matter itself, as we encounter it in stars and planets and the ground under our feet, is mostly emptiness at the fundamental level. The solidity of objects is an emergent property of electromagnetic forces between atoms, not a reflection of matter actually filling space. The table in front of you is not solid in the way it feels. It is a lattice of atomic nuclei surrounded by electron clouds, with electromagnetic forces creating the illusion of impenetrability. The universe is empty at cosmic scales. Galaxies are empty between stars. Stars and planets are empty at the atomic scale. The emptiness goes all the way down. And the matter we interact with, the planets, the stars, the galaxies themselves, is a very thin frosting, spread over an almost incomprehensible volume of nothing. There is one more layer to this that brings the whole picture into focus. The universe has been expanding since the Big Bang. Space itself has been stretching, carrying galaxies with it, increasing the distances between all structures not gravitationally bound to each other. This expansion is accelerating. Something astronomers call dark energy, making up roughly 68% of the universe's total energy content, and about which we understand almost nothing, is driving the expansion. Faster and faster. On large scales, this means the voids are growing. The cosmic web of filaments and galaxy clusters is being pulled apart by the acceleration of expansion. Distant galaxy clusters are moving away from us faster and faster. In the far future, trillions of years from now, the expansion will have carried all galaxies beyond the local group so far away that their light will no longer reach us. The observable universe will shrink to just our own gravitationally bound neighborhood. Everything beyond will be invisible, unreachable, effectively gone from our cosmic horizon forever. And within that shrinking observable universe, the same emptiness we see today will persist and grow. Even within galaxies, on the very long timescale of stellar evolution, the population of stars will eventually decline. Stars are born from gas. Gas gets used up. New stars become rarer. Over trillions of years, the stellar population of galaxies fades. The brilliant blue giants are already short-lived, burning out in millions of years. the medium-mass stars like our Sun last billions of years. The red dwarfs, the smallest, coolest, most numerous type of star, can burn for trillions of years on their tiny fuel budgets. But even red dwarfs eventually exhaust their hydrogen. And when the last stars go out at timescales so remote, it staggers the imagination. The galaxy will be a collection of stellar remnants in absolute darkness. White dwarfs cooling toward the ambient temperature of space. Neutron stars. Black holes slowly evaporating over unimaginably long periods. The emptiness of the galaxy will not change. But the sparse islands of light that populate it will, one by one, go dark. The galaxy will remain mostly empty space. Eventually, it will be entirely empty space. The emptiness is not a temporary condition awaiting filling. It is the fundamental nature of the universe matter, briefly concentrated by gravity in a thin frosting over an almost pure vacuum, and slowly dispersing again as the universe ages. When you look up at the night sky on a clear night, really look at it, away from city lights, away from screens, in a place where the Milky Way stretches overhead as a band of pale light, you are seeing the most concentrated part of the galaxy's stellar population. Every star you can see with your naked eye is within a few thousand light years. Most are within a few hundred. Individually resolved points of light against the black. And that band of the Milky Way, that soft, luminous river cutting across the sky, is not a dense wall of stars. It is the combined light of billions of stars in the disk of the galaxy, individually too far and too faint to resolve, but together producing a visible glow. You are looking along the plane of the disk, and the disk is thin, so the light piles up in that direction and produces the band. Look perpendicular to the disk, straight up out of the galactic plane, and the star density drops rapidly. In that direction, you are quickly out of the galactic disk and into the galactic halo, where stars are sparser still. And in every direction, in every gap between the points of light, in every patch of black sky between one star and the next, there is the emptiness. Light years of it. Trillions of miles of vacuum, drifting atoms, cold darkness, ancient photons from the Big Bang, still traveling through space, hundreds of thousands of years after they were released. The points of light are the anomaly. The darkness is normal. That has always been true. We are the ones who are new to understanding it. And understanding it changes how you see the galaxy. Not as a crowded city of stars, but as a vast, ancient wilderness where light years of cold, dark space separate the rare, warm places. The stars are the extraordinary exceptions. The emptiness is the ordinary state of things. There is something worth holding on to as we consider everything we've covered tonight. Stars, planets, and all the complex chemistry they enable exist in the universe only because of an enormously improbable chain of conditions. The universe had to begin in a state precise enough to produce the small density fluctuations that became the cosmic web. Gravity had to act on those fluctuations long enough to form galaxies. The galaxy had to exist in a state where the right proportion of gas could cool and collapse into stars. Stars had to live long enough and end dramatically enough in supernovas to forge and scatter heavy elements, carbon, nitrogen, oxygen, iron, into the interstellar medium. Those heavy elements had to find their way into new generations of gas clouds, enrich new stellar nurseries, and ultimately end up in planetary systems capable of building the chemistry of life. All of this happened But what the emptiness tells us is how much of the universe it did not happen in. For every star with a planetary system, there are light years of cold, empty space with nothing in them at all. For every galaxy, there are vast voids where galaxies are rare. For every atom that ended up in a planet or a living thing, there are countless more, drifting alone through interstellar space, never joining anything more complex than a molecule. The universe is extraordinarily productive in absolute terms. 2 trillion galaxies, each containing hundreds of billions of stars, each with the potential to host billions of worlds. The numbers are enormous. But the universe is also extraordinarily inefficient. It uses an incomprehensible volume of space and an incomprehensible proportion of its time to produce, in isolated pockets, the concentrations of matter and energy where interesting things happen. The emptiness is not evidence of waste. It is evidence of how hard it is to make something complex. How many vast volumes of nothing are required for every small warm place where matter organizes itself into something extraordinary. There is another dimension to galactic emptiness that most people never consider, and it has to do with time. We tend to think of the galaxy as a static structure, a fixed arrangement of stars in a disk, orbiting peacefully around the galactic center. But the galaxy is in constant motion at every scale, and the timescales over which that motion plays out reveal something profound about the relationship between space and time in an astronomical context. Our Sun, for instance, is not sitting still in its position in the Orion Spur. It is orbiting the galactic center at roughly 515,000 miles per hour. At that speed, it takes the Sun approximately 225 million years to complete one full orbit around the Milky Way. This period is sometimes called a galactic year or a cosmic year. And in the 4.5 billion years since the solar system formed, our Sun has completed roughly 20 of these galactic orbits. 20 laps around the center of the Milky Way since the Sun first ignited. But here is what is remarkable about this. Even moving at 515,000 miles per hour, it takes 225 million years to make one orbit. The galaxy is so large and the stars are so spread out that even at the extraordinary velocities involved in galactic rotation, crossing a significant fraction of the galaxy takes timescales measured in hundreds of millions of years. And as the Sun moves through the galaxy on its long orbit, it passes through regions of varying stellar density. Sometimes it moves closer to a spiral arm, where gas and young stars are more concentrated. Sometimes it drifts between the arms, in quieter space. The Sun's neighborhood, the specific collection of stars that are close to it at any given moment, changes over geological timescales. The stars that are our neighbors today are not the same stars that were our neighbors 200 million years ago. Each stellar system moves independently through the galaxy, following its own path around the center. Sometimes, paths bring stellar systems closer together. More often, they carry them apart. The apparent stability of the night sky, the sense that the stars are fixed, permanent fixtures in the heavens, is an illusion produced by the fact that our lifetimes are so short compared to the timescales on which stellar positions change. Over a human lifetime, the stars barely move relative to each other. Over millions of years, the entire stellar neighborhood rearranges. The sky our descendants will see, millions of years from now, will be fundamentally different from the one we see tonight. Different stars will be nearby. Different constellations will be visible. The galaxy's emptiness is not just spatial, it is temporal. The stars move through the empty space between each other, on timescales that dwarf everything in human experience. And the motion itself is a consequence of the same emptiness that defines the galaxy. If the stars were denser, gravitational interactions between them would be more frequent, orbits would be constantly perturbed, and the galaxy's dynamics would be far more chaotic. The emptiness is what allows the orderly, predictable orbital structure of the galaxy to persist. Planets can exist in stable orbits around their stars for billions of years, precisely because the nearest neighboring star is far enough away that its gravity barely perturbs the local system. If stars were even 10 times closer on average, the gravitational disturbances from passing stars would be far more common and far more severe. Planetary systems would be destabilized. Long-term orbital stability, a prerequisite for the kind of complex chemistry and biological evolution that produced us, would be far less common. The emptiness, again, is not incidental. It is a condition for the existence of stable worlds. One of the most striking illustrations of galactic emptiness comes from globular clusters, spherical collections of stars found in the galactic halo, orbiting the Milky Way at large distances from the disk. Globular clusters are, by galactic standards, genuinely dense. A typical globular cluster contains a few 100,000 to a few million stars, packed into a region just a few dozen to a few hundred light-years across. The densest globular clusters have stellar separations of fractions of a light-year in their central cores. By comparison, our neighborhood has separations of 4 to 5 light-years. In the most central regions of the densest globular clusters, stellar separations drop to light months, or even light weeks. This is dramatically denser than our local environment. And in those dense cores, the dynamics are fundamentally different. Stars interact gravitationally far more frequently. Close encounters between stellar systems are common on astronomical timescales. Planetary systems, if they formed there, would frequently be disrupted by passing stars. The probability of a star being physically close enough to another for tidal effects to become significant is much higher. But even in the densest globular cluster core, even in those extraordinarily packed stellar environments by galactic standards, the stars are still not touching. They are still separated by distances measured in light months. Light months. The amount of space that light covers in 30 days of constant travel at 186,000 miles per second. Even the densest stellar environments in the galaxy are emptier than anything we encounter in everyday life. The densest object you have ever touched is orders of magnitude denser than even the most crowded region of any known galaxy. Our intuition that dense means stars, close together, is built entirely for the wrong scales. Stars are never close together in any sense that would be meaningful to a human standing inside that space. They are always separated by distances that dwarf anything in our experience. The difference between a globular cluster and an open stretch of the galactic disk is the difference between 1 atom per cubic centimeter and 10 atoms per cubic centimeter in the interstellar medium. Both are effectively empty. The comparison just reveals a gradient of emptiness, not a range that includes anything we would recognize as crowded. The Milky Way has about 150 known globular clusters. Some of the most famous include Omega Centauri, the largest and most massive globular cluster associated with the Milky Way, containing roughly 10 million stars in a region about 150 light-years across. Omega Centauri is unusual in several ways. It is so large and complex, with multiple stellar populations of different ages and compositions, that some astronomers believe it may actually be the stripped core of a small galaxy, one that fell into the Milky Way long ago and had its outer stars torn away by tidal forces. Other notable globular clusters include 47 Tucanae, a dense, brilliant cluster visible from the southern hemisphere, and Messier 13, sometimes called the Great Hercules Cluster, visible to the naked eye on a clear night in the northern hemisphere. But even in Omega Centauri, even with 10 million stars packed into a region 150 light-years across, the stars are still separated by distances measured in fractions of a light-year to a few light-months in the densest central regions. Still, mostly space. Still fundamentally empty. Just less so than the open disk of the galaxy where our sun resides. Globular clusters are a reminder that the galaxy has internal structure at many scales, that emptiness and density vary depending on where you are. But they also demonstrate that even the cluster densest natural stellar environments in the galaxy remain overwhelmingly empty by any standard except the cosmic one. Now let's think about what this means for the prospect of life existing elsewhere in the galaxy. If the galaxy were denser stars packed closer together, the conditions for stable planetary systems would be less favorable. Gravitational disturbances from passing stars would be more frequent. Stellar radiation environments would be more intense and variable. The risk of a nearby supernova delivering a lethal dose of radiation to a neighboring planetary system would be higher. But the galaxy's current density has another implication for life that is less obvious. The composition of stars varies systematically across the galaxy. Stars that formed earlier in the galaxy's history, when only hydrogen and helium were available, are what astronomers call metal poor. They contain very few of the heavy elements that are essential for building rocky planets and the chemistry of life. Stars that formed more recently, after billions of years of stellar evolution, had enriched the interstellar medium with carbon, nitrogen, oxygen, iron, and dozens of other elements forged in stellar interiors and scattered by supernovas are metal-rich. The composition of the interstellar medium, the gas that forms stars, has been gradually enriched over time as successive generations of massive stars formed, lived, and ended in supernovas. Each cycle of stellar birth and ending added more heavy elements to the mix, and this enrichment has not been uniform across the galaxy. The galactic center, where star formation has been most intense and most sustained over the galaxy's history, is more metal-rich than the outer disk. The outer disk, where stellar density is lower and star formation has been less intense, has a lower heavy element abundance. Our sun sits in the middle disk, a location rich enough in heavy elements to allow the formation of rocky planets and the complex chemistry of life, but not so dense in stellar activity that the radiation environment or gravitational disturbances would be prohibitively hostile. This is sometimes called the galactic habitable zone, an annular region of the disk, where the combination of chemical richness and stellar density is most favorable for the emergence of life. It is a concept with real uncertainties, and the boundaries of the habitable zone are not sharp. But the general idea that the large-scale structure of the galaxy, including the distribution of matter and the history of star formation, at different distances from the center shapes where complex life is most likely to emerge, is a genuinely important insight. We did not end up in our specific location in the galaxy by some directed intention. But our location turns out to be one of the more hospitable places in the galaxy for the kind of chemistry that led to us. The emptiness of our neighborhood is, in a real sense, one of the conditions that made our existence possible. Let's take a moment to think about what the interstellar medium actually looks like in different regions of the galaxy, because the variation is remarkable and largely invisible to the naked eye. From Earth's perspective, the night sky appears as a smooth distribution of stars against darkness. But the interstellar medium is anything but smooth. It is a complex, turbulent, layered structure with features spanning enormous ranges of scale. The largest structures in the interstellar medium are the superbubbles, vast cavities of hot, thin gas created by multiple supernovas, spanning hundreds of light years. Inside these bubbles, the gas is hot and thin, temperatures of millions of degrees, densities lower even than the average interstellar medium. The local bubble, our own local example, is one of perhaps many thousands of such structures scattered across the galaxy. Our solar system is believed to be located within this local bubble, a region of relatively hot, thin interstellar gas carved out over the past few tens of millions of years by supernova explosions from a nearby group of massive stars. The bubble extends several hundred light-years in multiple directions, and its boundary is marked by a thin shell of denser gas where the supernova shockwaves have swept up material. Within and around the superbubbles are the warm phases of the interstellar medium neutral gas at temperatures of around 8,500 to 17,500 degrees Fahrenheit, or roughly 4,700 to 9,700 degrees Celsius. More diffuse than the cold molecular clouds, but denser than the hot bubble interiors. This warm phase is thought to make up a large fraction of the total mass of the interstellar medium. It is the background material of the galaxy, the medium through which everything else moves. Embedded in the warm medium are the cold, neutral clouds, denser regions at temperatures of around -279 degrees Fahrenheit, or -173 degrees Celsius, or colder. These cold clouds are the structures that can eventually cool further into the molecular clouds where star formation begins. And threaded through all of these phases, occupying the same space, are the magnetic fields. The interstellar magnetic field is extraordinarily weak by terrestrial standards, about 10 millionths of the strength of Earth's magnetic field. But because it permeates such an enormous volume of space, it plays a significant role in the dynamics of the interstellar medium, controlling how gas moves and how it can be compressed into star-forming regions. The interstellar medium is not a passive void. It is an active, dynamic environment constantly being stirred by supernovas, shaped by stellar radiation, threaded by magnetic fields, compressed by gravitational forces, and slowly feeding the ongoing cycle of star formation and stellar evolution. It is the medium through which the galaxy breathes, and it is, in mass terms, a small fraction of the galaxy's total mass, most of which is in the stars themselves and the invisible dark matter halo. The interstellar medium that fills the spaces between stars that thin, cold, mostly empty gas represents perhaps 10 to 15% of the galaxy's visible mass. The stars represent the rest of the visible mass, and the dark matter halo outweighs both by a factor of several. The galaxy is mostly dark matter. Of the luminous matter, most is in stars. And the space between those stars, the interstellar medium, is a small fraction of a small fraction. Yet that small fraction is the nursery of all future stars, the graveyard of all past ones, and the environment through which every stellar system in the galaxy moves during its billions of years of existence. For most of the 20th century, astronomers assumed that the rotation of galaxies was something they broadly understood. Stars and gas, orbiting a central mass. The same physics that governs planets, orbiting a star. And if the physics was the same, the predictions were straightforward. Stars farther from the center, where most of the galaxy's mass is concentrated, should orbit more slowly than stars closer in. This is what we see in the solar system. Mercury, the innermost planet, whips around the Sun in just 88 days. Neptune, far out in the cold dark, takes 165 years. The orbital speed decreases with distance from the central mass. This was expected to be true for galaxies as well. But when astronomers in the 1960s and 70s, most famously Vera Rubin and her colleagues, measured the actual orbital velocities of stars at different distances from galactic centers, they found something deeply wrong with this picture. The stars in the outer regions of galaxies were not slowing down as expected. They were moving just as fast as the inner stars. In some cases, the rotation curve, the graph of orbital speed versus distance from center, was essentially flat out to the visible edge of the galaxy and beyond. This should be impossible if only the visible matter were providing the gravity. For the outer stars to orbit that fast, there had to be enormous amounts of additional mass that we couldn't see. Not a small correction. Not a 10% adjustment. The invisible mass had to be several times the total mass of all the visible stars and gas combined. This was the accumulating body of evidence that led to the now accepted concept of dark matter halos surrounding galaxies. The flat rotation curves of galaxies are one of the most robust and reproducible results in observational astronomy. They have been measured for hundreds of galaxies across a wide range of types and sizes, and they all tell the same story. Galaxies contain far more mass than we can see, and that mass extends well beyond the visible stellar disk in a vast, spherical halo. The dark matter halo is not evenly distributed. It is denser in the inner regions and thins out at larger radii. But it is present in significant quantities throughout a volume much larger than the visible galaxy. And because dark matter interacts only through gravity, not through any electromagnetic interaction, it passes through both ordinary matter and other dark matter with essentially no interaction. Dark matter halos of different galaxies can interpenetrate during galaxy mergers, each dark matter distribution passing through the other and then settling into a combined halo around the merged system. This has been directly observed in galaxy collision systems, like the Bullet Cluster, two galaxy clusters that have passed through each other, with the hot gas from each cluster colliding and slowing, while the dark matter halos passed through each other relatively unimpeded. The separation between the gas and the dark matter after the collision provides some of the most direct evidence we have for the existence of dark matter as a distinct component of matter that does not interact electromagnetically. So when we say the galaxy is mostly empty, the full picture includes this invisible component. The visible space between stars is nearly empty of ordinary matter, but it is not empty of dark matter. Dark matter permeates the entire halo of the galaxy, extending hundreds of thousands of light years in every direction. We can't see it. We can barely detect it. But it is there, providing the gravitational scaffolding within which the visible galaxy exists. The emptiness we can see is real. But beyond and around and through that emptiness, something we cannot see fills an even vaster volume with a gravitational presence that shapes everything we observe. There is one final aspect of the galaxy's emptiness that is worth sitting with before we reach the end of tonight. It has to do with what the galaxy would look like if you could see it from far outside. If you were positioned hundreds of millions of light years from the Milky Way, looking at it from above, from a perspective perpendicular to the galactic plane, what would you see? You would see a disk of light. A flat, roughly circular structure with a bright central bulge and fainter spiral arms extending outward. The overall appearance would be something like a lens, bright and concentrated at the center, thinner and dimmer at the edges. And from that perspective, the Milky Way would look full of stars. The combined light of 200 billion to 400 billion stars compressed into a flat disk that spans 100,000 light-years would produce a luminous structure visible across enormous distances. This is what we see when we look at other spiral galaxies. Andromeda, 2.5 million light-years away, is visible to the naked eye from a dark sky as a faint smudge. With a telescope, we can see its structure, the central bulge, the disk, the faint spiral arms. It looks like a coherent, luminous object. It does not look mostly empty. But that appearance is the combined light of hundreds of billions of point sources, averaged over the enormous distance separating us from each one. What looks like a continuous glow is actually individual stars separated by light years, their light blended together by the distance between us and them. The apparent solidity of a galaxy viewed from a distance is an optical illusion produced by the sheer number of sources and the angular compression caused by the distance. If you were inside Andromeda, if you were standing on a planet orbiting one of its stars, you would see exactly what we see from Earth. Stars scattered across the sky, separated by vast distances, the equivalent of the Milky Way visible as a band of light in one direction, and in every other direction, darkness between the stars. The continuity is a perspective effect. The reality is emptiness, punctuated by isolated points of light. Every galaxy that looks full and solid from the outside is, from the inside, almost entirely nothing. This is one of those facts that is genuinely difficult to hold in your mind once you understand it. The beautiful galaxies in astronomical photographs, those luminous spirals and ellipticals and irregulars that look like solid structures made of light, are actually incredibly sparse. Collections of tiny stellar objects separated by enormous voids. The beauty is real. The apparent solidity is not. Each one of those galaxies is almost entirely the space between the things that produce the light. And yet, for all that, for all the emptiness, for all the scale, for all the near nothingness that characterizes the vast majority of galactic volume, the light still travels. It crosses those enormous voids. It arrives at other stars, other worlds, other places where conditions might have allowed matter to organize itself into something that can receive it. The light from our sun is currently traveling outward in all directions at 186,000 miles per second. 4 years from now, some of it will reach Proxima Centauri. Thousands of years from now, some of it will reach stars near the galactic center. Millions of years from now, some of it will reach galaxies in the local group. The light crosses the emptiness, because that is what light does. It travels through space and does not slow down and does not stop, and it carries information about the place and time it came from. Every star in the sky is sending its light across the void. And from every one of those stars, if any world orbits it with the right conditions, that light could be the same thing to some other observer. That starlight is to us a signal from a warm, isolated place in an ocean of cold and dark, carrying the information that something interesting is happening here. We do not know if anyone else is receiving that signal. We do not know if any other world in this galaxy looks out at the emptiness and wonders about it the same way we do. But the emptiness does not care either way. It stretches between the stars, regardless of whether anyone is there to notice it. It has been stretching since before the first stars formed, and it will continue stretching long after the last ones go dark. We are temporary concentrations of matter in an overwhelmingly empty universe, briefly organized enough to measure the emptiness and find it astonishing. That is a remarkable thing to be. There is something worth exploring about the particular emptiness of open star clusters and how they compare to both globular clusters and the general galactic disk, because they reveal how star formation naturally produces isolated stellar systems even when stars are born together. Open star clusters form when a region of a molecular cloud collapses and produces many stars in a relatively short time. A molecular cloud might give birth to hundreds or even thousands of stars within a few million years, all forming from the same reservoir of gas, all emerging into the same region of space. When those stars first form, they are genuinely close together by stellar standards. The newly formed stars in a young open cluster might be separated by a fraction of a light year, much closer than the average galactic spacing. Young open clusters, like the Pleiades, that familiar tight grouping visible to the naked eye in the constellation Taurus, formed roughly 100 million years ago and still contains several hundred stars within a region about 43 light-years across. The Pleiades are close enough together that from within the cluster, the stellar density would be noticeably higher than in our current neighborhood. More stars would be visible at brighter magnitudes. The night sky from a planet inside the Pleiades would be richer, more crowded than our own. But the Pleiades will not stay that way. Open star clusters are not gravitationally stable over long timescales. They are loosely bound. The gravitational pull holding them together is relatively weak, and over hundreds of millions of years, gravitational interactions with passing molecular clouds, with the tidal forces of the galaxy itself, and with the individual dynamics within the cluster, gradually pull the stars apart. The cluster disperses. Its member stars drift into the general disk population, each one following its own independent orbit around the galactic center. Over time, the stars that were once siblings, born from the same cloud, young together scatter across the galaxy, separated by the same light-year gaps that characterize all stellar neighbors. The solar system may itself be an orphan in this sense. Our Sun formed about 4.5 billion years ago in a cluster that has long since dispersed. Astronomers have searched for the Sun's birth cluster, the stellar siblings that formed alongside it from the same molecular cloud. Some candidate stars have been identified based on their compositions, ages, and orbital histories, but the original cluster is gone, scattered across the galaxy over billions of years. The Sun is now alone in its neighborhood, as it has been for essentially all of recorded history. Its birth companions separated from it by the same emptiness that defines all stellar distances. Every star you see in the night sky is, in some sense, a former member of a birth cluster that has long since dissolved. The stars we see scattered individually across the sky were not always so isolated. They were born in groups. But the galaxy's tidal forces and the passage of time disassembled those groups, leaving each star to wander independently through the galactic disk. The emptiness between stars is, partly, the record of that dispersal, of clusters born dense and pulled apart over billions of years. of siblings separated by the galaxy's inexorable dynamics. The current emptiness is partly a consequence of the fact that galaxies are old enough for birth clusters to have dissolved and scattered. In a younger galaxy in the early universe, when the first star-forming events were still underway, stellar groupings would have been younger and denser. More of the stars would have still been close to their birth companions. But over time, the galaxy shuffles its stars. It mixes them. It separates them. And the result, 4.5 billion years into our solar system's history, is the nearly uniform, nearly empty distribution of stellar neighbors we see today. There is a scale of emptiness in the galaxy that sits between the emptiness of the stellar neighborhood and the emptiness of intergalactic space, and it is often overlooked. The galactic halo. The halo of the Milky Way is a vast, roughly spherical region surrounding the disk, extending out to perhaps 100,000 light-years from the galactic center in all directions. The halo is not empty in the sense of containing nothing at all. It contains old stars, some of the oldest stars in the galaxy, formed in the early universe before the disk had settled into its current flat structure. It contains the globular clusters, those ancient dense balls of stars orbiting the galactic center in wide, tilted paths. And it contains what astronomers call halo stars, individual stars moving through the halo on similarly wide, tilted orbits that carry them far from the disk. But the halo is very sparse. The stellar density in the halo is enormously lower than in the disk. In the disk, in our neighborhood, there are perhaps a few tens of stars per 100 cubic light-years, already a fantastically low density. In the halo, the stellar density drops to a tiny fraction of even that. The halo stars are scattered across an enormous volume, with separations that can be hundreds or thousands of light-years. And the halo volume is vast. A sphere of 100,000 light-years radius contains an enormous amount of space, most of it effectively empty of stars. Above and below the galactic disk, perpendicular to the plane in which the spiral arms sweep, the stellar density drops away relatively quickly. Within a few thousand light-years above or below the disk, you have moved out of the main stellar population. The stars thin out dramatically, and by the time you are tens of thousands of light-years above or below the galactic plane, you are in the deep halo, a region where individual stars are rare and widely separated. Between the halo stars, there is essentially nothing. Not even the thin interstellar medium that fills the disk. The halo is filled with something even more diffuse, a very thin, very hot plasma of gas at temperatures of millions of degrees, heated by supernova explosions and the energy released by the disk's star-forming activity. This hot halo gas is so thin that it is virtually undetectable by most observational methods. But it is there, confirmed by ultraviolet and X-ray observations that reveal the emission and absorption of this ultra-diffuse plasma. Even in the halo, even in that most sparse environment, above and below the disk, the galaxy is not completely empty. But it is closer to empty than anywhere in the disk. The halo is the galaxy fading into the background of the universe. Below the halo's outermost boundary, even the dark matter halo thins out and eventually merges with the general dark matter distribution of the universe. The galaxy has no sharp edge. It simply becomes progressively emptier in every direction until its identity as a distinct structure merges with the larger structures of the cosmic web. One of the most remarkable observations in modern astronomy is the detection of what are called high-velocity clouds, enormous structures of neutral hydrogen gas moving through the galactic halo. at speeds inconsistent with normal galactic rotation. These clouds can be millions of times the mass of our Sun and extend for tens of thousands of light years. Some of them are falling inward toward the disk, accreted from the intergalactic medium or the remnants of past interactions with satellite galaxies. Others may be gas that was expelled from the disk by supernova-driven winds and is now falling back. The Magellanic Stream is one of the most dramatic examples, a vast ribbon of gas stretching across a large portion of the sky, pulled from the large and small Magellanic Clouds by the gravitational tidal forces of the Milky Way. The Magellanic Stream extends for more than 140 degrees across the sky, containing roughly 200 million solar masses of gas, enough material to form billions of stars if it ever collapses into the disk and triggers star formation. These high-velocity clouds reveal that the galactic halo is not a static, empty region between the disk and intergalactic space. It is a dynamic environment where gas is constantly moving, accreting from outside, being expelled from the disk, swirling around in complex orbits shaped by the galaxy's gravity and the remnants of past interactions. And yet, even with all this gas moving through the halo remains almost completely empty by any standard except the astronomical one. The total mass of gas in the high-velocity clouds is only a small fraction of the galaxy's total gas content. The gas is spread across enormous volumes. And between the gas clouds, even in the regions where the clouds are most concentrated, the density is extraordinarily low. The halo, like the disk, is defined by its emptiness. Structure exists within it. But the structure occupies a tiny fraction of its volume. Now, let's think carefully about what observations have taught us about the interstellar medium in the specific context of star formation, because the details reveal something important about the relationship between emptiness and complexity. When a molecular cloud begins to collapse, it does not do so smoothly and uniformly. The collapse is turbulent and hierarchical. Turbulence within the cloud creates density variations on many scales simultaneously. Some regions reach the critical density for collapse before others. Those regions fragment and collapse independently, while surrounding areas remain too diffuse to form stars. The process produces a fractal-like structure, dense cores embedded within denser clumps, embedded within more massive cloud fragments, embedded within the overall molecular cloud. At each level of the hierarchy, only the densest regions actually form stars. The surrounding material at each level is too diffuse, too disrupted by turbulence, too supported by magnetic fields or thermal pressure to collapse. The result is that even within a molecular cloud, which is already one of the densest environments in the interstellar medium, the fraction of volume occupied by actual star-forming regions is tiny. The regions that form stars are highly concentrated, dense cores surrounded by much larger volumes of less dense gas that will not form stars. And when the stars form and begin to radiate, their light and winds rapidly disperse the surrounding gas, halting further star formation in the immediate vicinity. The process is self-limiting. Stars form, and in forming, they prevent more stars from forming nearby. The net result, averaged over all the molecular clouds in the galaxy and all the epochs of star formation since the galaxy assembled, is the current stellar distribution. Hundreds of billions of stars, each one surrounded by light years of space, the product of billions of years of this self-limiting, hierarchical collapse process operating on a dilute sea of gas spread across an enormous disk. The emptiness between stars is the sum of all the regions that never collapsed. All the gas that was too warm, too turbulent, too magnetically supported, too disrupted by nearby star formation to condense into a star. The empty light years between stellar systems are the silent testimony to every cloud that never collapsed, every core that never ignited, every fragment of gas that drifted rather than falling. The stars are the exceptions to the rule of diffuse gas. And the diffuse gas is the exception to the rule of complete emptiness. And the complete emptiness is the rule. Here is a perspective that rarely gets discussed, and it reframes the entire story of galactic emptiness in a way that is genuinely striking. From a physics standpoint, the universe is not empty by accident. It is empty by necessity. The laws of physics, specifically, the laws governing gravity, thermodynamics, and nuclear physics constrain what forms matter can take and how efficiently it can concentrate. Gravity pulls matter together. But as matter concentrates, other forces push back. Thermal pressure in gas, clouds. Radiation pressure from newly formed stars. The centrifugal effect of rotation. Magnetic fields threading through the gas. The interplay of all these forces determines how concentrated matter can become and on what timescales. The result, in a universe that started dense and has been expanding and cooling for almost 14 billion years, is the current distribution. Matter concentrated into isolated, hot, dense objects, stars surrounded by cold, thin, nearly empty space. The stars represent the maximum concentration that the relevant physics allows to be stable over long timescales. Denser concentrations like white dwarfs and neutron stars exist, but they are remnants of stellar evolution, not the primary large-scale structures of the galaxy. The most massive objects, black holes, are even denser, but they represent the extreme endpoint of collapse, not the typical state of matter. For the typical matter in the galaxy, the typical state is a star. A ball of plasma burning hydrogen into helium, in hydrostatic equilibrium between gravity pulling inward and thermal pressure pushing outward. And between stars, the typical state is near vacuum. Too diffuse for star formation, too warm for collapse. Maintained in its diffuse state by the energy output of the stars surrounding it. The galaxy has reached, in a rough sense, a steady state. A balance between the forces that drive star formation and the forces that prevent it. The stellar density is what it is because the physics of gas dynamics, radiation, and gravity have settled the system into this configuration. Change the physics, make gravity stronger, make gas cooling more efficient, make radiation pressure weaker, and the stellar density would be different. The galaxy would be fuller or emptier, depending on which way the balance shifted. But in our universe, with our laws of physics, the balance lands where it does. And where it lands is mostly empty space, punctuated by rare, isolated points of stellar fusion. The emptiness is written into the laws of the universe, not imposed arbitrarily. It is the natural outcome of physics acting on matter across cosmic time. There is something worth dwelling on about how the galaxy's emptiness is experienced differently depending on where within it you happen to be, not just in terms of stellar density, but in terms of the specific environment created by that density. Consider the difference between being a star system embedded in the dense core of a young star cluster versus being a star system like our own, isolated in the inter-arm regions of the galactic disk. In the dense core of a young cluster, the stellar radiation environment is intense. Massive blue stars nearby pour out ultraviolet radiation at rates thousands of times higher than our sun's output. The interstellar medium between those stars is ionized and energized. High-energy particles stream through the space between stellar systems at elevated rates. Supernovas, when the massive stars end their lives, send shockwaves through the surrounding space that compress and heat everything nearby. It is a dynamic, active, energetic environment. And that energy is, ultimately, a form of filling the space with radiation and particle flux and shockwaves that would be lethal to most biology as we understand it. The emptiness in a young star cluster is filled with energy, even if it contains very little mass. In our quiet inter-arm neighborhood, the situation is very different. The nearest massive star to our sun is hundreds of light years away. The radiation environment is orders of magnitude calmer. The particle flux from cosmic rays is lower. Supernovas, when they do occur, are far enough away that their shockwaves have dissipated significantly before reaching our solar system. The emptiness here is cold and quiet. The interarm regions of the galaxy are, in energy terms, closer to actual emptiness than the spiral arms. They are darker, quieter, less energetically filled. And this quietness is part of what makes them hospitable. A planetary system in the quiet interarm regions has a much calmer radiation environment over billions of years than a system embedded in an active spiral arm or a dense cluster. The biological implications of this are significant. Complex biochemistry requires long timescales and stable energy environments. Evolution requires geological time, billions of years of consistent conditions. A planetary system that is repeatedly struck by nearby supernova shockwaves or bathed in intense ultraviolet radiation from neighboring massive stars faces constant disruption. The emptiness of our neighborhood, its quietness, its relative isolation, its distance from the dramatic events that light up the spiral arms is one of the reasons our sun has been able to provide stable conditions for life over 4.5 billion years. We live in one of the emptier, quieter corners of the galaxy. And that emptiness may be inseparable from the fact that life exists here to notice it. The relationship between galactic emptiness and the observable universe is worth tracing out to its full extent, because it reveals something important about the nature of observation itself. When we look at the night sky, we are looking through the emptiness of the galaxy. Every star we see through light years of nearly empty interstellar space. The light from each star has traveled through that space, through the thin interstellar medium, carrying information about the star's temperature, composition, and motion. But the interstellar medium is not perfectly transparent. There is dust, tiny grains of carbon and silicate minerals, microns in size, distributed through the cold neutral regions of the interstellar medium. This dust absorbs and scatters starlight, particularly at blue wavelengths. The dust is not thick. The interstellar medium is still incredibly sparse, but over distances of thousands of light years, even a tiny density of dust grains produces significant extinction. This is why we cannot see the galactic center in visible light. Between here and the galactic center, 26,000 light-years of interstellar medium contains enough dust to absorb essentially all of the visible light from that direction. The galactic center is hidden from our optical telescopes behind a curtain of dust. To see it, we have to use infrared and radio observations, which penetrate the dust far more effectively than visible light. The infrared and radio photographs of the galactic center reveal the dense concentration of old stars in the bulge, the molecular clouds surrounding Sagittarius A, and the complex dynamics of gas orbiting the central supermassive black hole. This is a direct consequence of the galaxy's structure, its composition, the distribution of gas and dust through its volume, the physics of how light interacts with matter at different wavelengths. And it is a reminder that the emptiness of the galaxy, while real and profound, is not absolute. Even the thin veil of dust distributed through the nearly empty interstellar medium is enough to block our view of the galaxy's heart at visible wavelengths. The near emptiness matters. It is not quite the same as true emptiness. And the difference is visible, or rather, the difference is what prevents visibility. Infrared astronomy opened a window through the dust. Radio astronomy opened another. X-ray and gamma-ray astronomy opened more. Each wavelength range reveals a different aspect of the galaxy's structure, because each interacts differently with the thin, sparse material distributed through the nearly empty interstellar space. The emptiness of the galaxy, studied in detail, turns out to be one of the richest and most complex objects in the observable universe, a multi-layered, multi-phase, dynamically active medium that connects every star in the galaxy and shapes the history of each one. There is a final thought worth carrying through all of this, one that connects the emptiness of galaxies to the deepest questions about what kind of universe we live in. The universe is, by volume, overwhelmingly empty. 80% of its volume is in the cosmic voids. Of the remaining 20%, most is in the filaments and walls of the cosmic web, where the density of matter is still extraordinarily low by any terrestrial standard. Of the matter in those filaments, most is dark matter invisible, undetectable by any means except its gravitational effects. Of the ordinary matter in the filaments, most is in the form of hot, diffuse gas in galaxy clusters, and galaxy halos spread thin across enormous volumes. Of the ordinary matter that has condensed into galaxies, most is in the form of dark matter halos and thin interstellar media. Of the ordinary matter that has condensed into stars, most is in the form of cool, dim red dwarfs, the most numerous type of star in the universe. Each one a tiny ember compared to our sun. And of all the planets orbiting all the stars in all the galaxies in the observable universe, the fraction that have the right conditions for the kind of complex chemistry that leads to self-replicating molecules and evolution and eventually consciousness, that fraction is unknown. But it is almost certainly small. The universe is extraordinarily good at producing large amounts of nothing. It is extraordinarily selective about where and when it allows the complex to emerge. We are, at every scale of description, an improbable concentration of organized matter in an ocean of disorganized nothing. And we have the capacity to understand that, to map the emptiness, to measure it, to trace its origin in the quantum fluctuations of the early universe and its future in the accelerating expansion driven by dark energy, to understand why the stars are spaced as they are, why the galaxy has the structure it does, why the interstellar medium has the composition it has. To look out at 2 trillion galaxies in the observable universe, each one mostly empty, all of them together, occupying only 20% of the cosmic volume, and understand what we are seeing. That capacity for understanding is itself one of the most improbable concentrations of organization in the known universe. The matter that makes up a human brain, the carbon and nitrogen and oxygen and hydrogen and trace elements, organized into neurons and synapses, and the electrochemical patterns that constitute thought, represents a level of organization that requires precisely the right conditions over precisely the right timescales. It requires stable planetary orbits over billions of years. It requires the quiet radiation environment of an interarm stellar neighborhood. It requires chemistry that was only possible after multiple generations of stellar evolution had seeded the interstellar medium with heavy elements. It requires, in the end, a galaxy that is mostly empty, that has the right structure, the right stellar density, the right radiation environment, the right chemistry in the right locations. The emptiness made us possible, and we made the emptiness observable. That is, in the end, what tonight is really about. Not just the fact that galaxies are mostly empty, though they are, and profoundly so, but the fact that the emptiness and the life it enabled are two sides of the same cosmic story. The universe made emptiness the rule, and matter the exception. And in one exceptional pocket of one exceptional galaxy, the exception became complex enough to understand the rule. And perhaps that is the most remarkable thing about all of this. Not the emptiness itself, that is just physics, just the way matter organizes itself under gravity in a universe that started dense and has been expanding and cooling ever since. The remarkable thing is that in this galaxy that is overwhelmingly empty space, on one of hundreds of billions of planets, orbiting one of hundreds of billions of stars, separated from each other by light years of cold, dark vacuum, a collection of atoms organized itself into something that could look out at the emptiness and ask why it exists. We are made of the same hydrogen that fills the interstellar medium, the same material that condensed into stars and then scattered back as those stars ended, the same atoms that drifted through the galaxy for billions of years before finding their way into the solar system as it formed. The carbon in our cells was forged in stellar cores. The iron in our blood came from supernova explosions. We are, in the most literal sense, small concentrations of galactic material that became temporarily organized enough to notice the galaxy around them. And the galaxy, for all its hundreds of billions of stars, for all its light years of luminous structure, is almost entirely the space between us and them. The emptiness is not a failure of matter to fill space. It is the canvas on which all of this, the stars, the planets, the cold interstellar gas, the dark matter halos, the ancient cosmic web is painted. And it is the understanding of that canvas, that overwhelming vastness of nothing, that makes the small, bright islands of matter so extraordinary. They exist at all against such odds, against such an ocean of cold and dark. And one of them, one unexceptional star among hundreds of billions, happened to form a system where the conditions were right, and the time was long enough, and the chemistry was complex enough for the emptiness itself to be noticed and understood. That is where we are. Out here, in the suburbs of an ordinary galaxy, surrounded on every side by more nothing than we could ever cross. Looking out, asking questions, finding answers, and finding that the answers, real, measurable, scientific answers, are stranger and more astonishing than anything we might have imagined. The galaxy is mostly empty. And the fact that we know that, from our small, warm corner of it, is everything. Good night.